All right, so we'll get started. Thank you everyone for attending this seminar. I'm very happy that you've asked me to give a revised version of the talk that I gave earlier this year. It's a critical evaluation of the climate and solar variability hypothesis. So to begin with, I want to make this following observation. Enceladus, which is a moon of Saturn, is like Earth without the sun. Right? If Earth were out at the location of Saturn, it too would be a frozen snowball, just like Enceladus. So at a very fundamental level, it really is the case that the sun determines Earth's climate. Right? We get the vast majority of the energy that we experience at Earth's surface, we get that from the sun, ultimately from the sun. But at the same time, Earth would be like Enceladus if it didn't have CO2. So even at the location where Earth is, if we were to pull out the CO2 in Earth's atmosphere, it too would become a frozen snowball, just like Enceladus. So because I've framed this discussion as a hypothesis test, then I'm going to tell you what my Bayesian prior is, and I'm going to make some distinctions here. So first of them, when is solar variability of first order importance, and when it isn't? So in my Bayesian prior, I believe that solar variability is important on stellar evolution timescales, so on billion-year timescales. So as the sun will become brighter over billions of years, which we know from looking at other stars and their evolution out in our galaxy and in the universe, then we know that the sun will increase its brightness over time. And so this is very important for Earth's past climate. It's going to be extremely important for Earth's future climate, especially in about 1 billion years when Earth will enter a runaway greenhouse state where it will actually evaporate. It'll be so much sunlight that will actually evaporate Earth's oceans, and we'll lose those oceans and ultimately lose that water. And so Earth will become a radically different place, an unlivable place within 1 billion years. The other is the ice age cycles. So over the past 3 million years, there have been very fascinating ice age cycles. We call these the Milankovitch-driven ice age cycles. And so this is basically the changes in seasonality and the distribution of sunlight that Earth receives depending on changes in the orbital parameters of Earth. So for example, the eccentricity. So how much the orbit of Earth is circular, how much it moves out of being circular changes over time. Its tilt changes over time, actually precesses like a spinning top over time. And so all of these factors change the distribution of sunlight over time. And so this can actually have the impact of changing where you can grow and destroy ice sheets. And so this has driven the ice age cycles over the past 3 million years. So these are the circumstances in my Bayesian prior where I believe that solar variability is of first order importance. And when is it not? Every time else. All right, so why do I believe that? So let's start off with just basic facts about solar variability based on what is observed. So solar variability, it creates an oscillating about plus or minus half a watt per meter squared. If you spread that all over the Earth, that's about 0.1 watts per meter squared. So we need to divide by 4 for accounting for the ratio of Earth's disk area to its surface area. And this quantity is indicated by the blue line. So this is total solar irradiance. So this is the amount of energy that Earth is receiving. And so this is what is oscillating up and down. And so it's actually the case that this total solar irradiance is impacted by variability in the output of the sun, and that this actually has an influence on something else, which are cosmic rays reaching Earth. So we can see an inverse relationship between the blue line and the orange line, which are neutron counts. So these are based on neutron monitors that give us an indicator, a very good indicator of cosmic rays that are hitting Earth. And so the sun does modulate this cosmic rays that are reaching Earth. So these two quantities, we'll be discussing this over the course of this talk. Okay, so 0.1 watts per meter squared, how does that compare to other radiative forcings? So in this plot, this is from the IPCC report from 2021, and is showing the different major factors of radiative forcing over time. And so what we can see from this is this 0.1 watts per meter squared is actually an order of magnitude smaller than first order factors, like what have been carbon dioxide emissions, or what have been volcanic eruptions, which are in the black, these kind of the big spiky signal that you see, or like the tropospheric aerosols. So these are human emitted aerosols. So these first order factors are an order of magnitude larger than what we see from solar variability. Then if we look at the time series of solar variability and compare that to global warming, and I'm showing here monthly data for all of these variables, if we compare the time series variability in the total solar irradiance as well as the cosmic rays, what we see is it just doesn't obviously explain global warming. So if we have an oscillating signal, but it's not a trending signal, and so it's not obvious that this has anything to do with explaining global warming. So that's enough of my Bayesian prior. Now we're going to get into the specific hypotheses, and it's basically a two-part hypothesis. So the first part of this hypothesis that has been proposed that I'll be addressing is that solar variability is the dominant driver of climate over the Phanerozoic. So figures such as the following, which we're going to get into in more depth, have been produced to argue that this is the case, that over the past 500 million years, the dominant driver of climate variability has been cosmic ray flux. Okay, the second part of this hypothesis that I'll be addressing is that solar variability has caused 1/2 to 2/3 of the observed global warming. So what are the mechanisms that could be causing this? So we'll go in detail in each of these. But the first one, if we start with mechanism A, this is due to the idea that solar variability in the ultraviolet is about 5 to 10 times larger, the variability within the visible wavelength. So it's still an oscillating signal. It's just the case that the variance is larger. Another mechanism that has been proposed is a direct effect of the total solar irradiance. And so mostly this has been looked at for the ocean. So we would expect that a radiative imbalance, that 90% of that imbalance will go into the ocean. And so it's reasonable to expect that we would see this signal in the ocean. So this is why people have focused on looking at this mechanism as it pertains to the ocean. Okay, the third potential mechanism that we'll be discussing is how galactic cosmic rays could co-vary with aerosols or something called cloud condensation nuclei, CCN. All right, so the first hypothesis, I'm going to break it down actually into a slightly simpler hypothesis and simply ask the question, is solar variability the dominant driver of paleoclimate? And we're going to look at some shorter timescales before we move out to the Phanerozoic timescales. So exhibit A in this argument, if you look at review papers, look at presentations that have been given on this subject, is this following speleothem from Hoti Cave in Oman. And so the speleothem is the measurements of delta 18O. This is the bottom time series, the darker gray time series. And what folks have done is then correlated in this original paper the delta 18O signature that was measured from the speleothem in Hoti Cave in Oman that grew from about 9,500 years ago to about 6,000 years ago. They correlate that with the delta 14C record. And so delta 14C in general is a cosmogenic nuclide. It depends on cosmic ray flux, which itself is modulated by solar variability, which is what we saw in one of the first slides. But C14 is also modulated by the state of Earth's magnetic field. It's also modulated by Earth's carbon cycle, both the global carbon cycle as well as the local carbon cycle. And so in order to then say, is delta 14C, is this a proxy for solar activity? You also need to have a good handle on what Earth's magnetic field is, as well as Earth's carbon cycle. So the people who have presented this as exhibit A for the hypothesis that solar variability drives climate have said, look at this fabulous correlation. this is great evidence in behalf of our hypothesis. Now, I went to actually reproduce this result with an updated delta 14C curve. So this is actually an extremely important curve. It's used in geochemistry, it's used in archaeology for carbon dating. And so every few years, it is updated to improve the quality of the data. So when I went to reproduce this result with the same cave and the updated data, correlation went away. So what did we learn from this? Well, we learned that sometimes the correlation goddess gives, and sometimes the correlation goddess takes away. But in general, this is a kind of dangerous thing to be doing. And so why is this dangerous? Because paleoclimate data is fundamentally noisy. So if we take, for example, signal, a time series, let's say it goes from the year 1000 to 2000, and this particular time series is directly what would be observed. Now, if we take some noise at different levels, we're going to add this noise to the signal and the levels that are appropriate for paleoclimate data. So the first example I'm showing here is a variance of 1, a variance of 4, and then we see a variance of 16 that we could add to this original signal. So then when we add the noise to the signal, then we get something that you would actually observe when you are making your measurements of the paleoclimate proxy, given paleoclimate proxy. So signal to noise ratio of 1 is equal variance between the signal to the noise. And then if we go all the way down to signal to noise ratio of 0.25, this is a variance that is 4 times larger of the noise compared to the signal. Now this just so happens to be the average among annual proxy data is the signal to noise ratio of 0.25, where the noise is 4 times the variance of the signal. So it is true that there is a small subset of proxies that are around signal to noise ratio of 1 or a little bit better, but the vast majority are far more noisy. And on average, it's 0.25. Many are even worse than this. So let's walk through an example of why this might be an example using a data set that I've used in several projects. So this is a data set that covers the Common Era, approximately 3,000 proxies. And what do we see here? We see lots of noise. So if we're going to find, correlate some time series with the paleoclimate proxy data in here, it's possible to find a correlation with a lot of stuff given this noise. So it's actually possible here, I claim, to find a paleoclimate proxy that correlates with almost anything. The almost anything needs to have some features that share with proxy data. It needs to be fundamentally like an autoaggressive process, because that's what paleoclimate proxy data fundamentally is. So let's look at an example. Number of world wars. What does it correlate with? Well, these tree rings in Vermont. So if you want to make predictions about the number of world wars that are going to happen in the future, just go core this stand of trees in Vermont. Let's look at another example. So UK exports as a share of GDP. Tree rings in Alaska did a fabulous job of capturing the variability in UK exports in the 1800s, and then at exactly the right time, they know that World War II is happening, they know that UK exports are going to go down during World War II, and that they'll make a gradual improvement as World War II finishes and the UK recovers from World War II. We don't have to stop in the UK. Let's look at Brazil. Brazilian exports as a share of GDP. Well, it matches this tree ring series from Connecticut beautifully. It captures this drop from the mid and late 1800s to the present very beautifully. So just because you find a correlation, even a correlation that looks really good with your paleoclimate proxy, does not mean it means anything. All right, so the first hypothesis. Over Phanerozoic timescales, is cosmic ray variability the dominant driver of climate? Now, it's reasonable to presume that the cosmic rays will change over time because our galaxy is actually warped and it wobbles. So I'm showing here a simulation of the galactic disk in our solar system as a black dot kind of going around and around the galactic disk. So over the galactic year, 225 million years, it takes the time it takes to go all the way around our galaxy. Then given this wobble and this warp, we might expect there to be variability in the cosmic ray flux. But there are a lot of unknown parameters in these cosmic ray flux models. So in this paper from 2003, the authors used a cosmic ray flux time series that they shifted. They looked at different phases, different amplitudes to try to fit that with the paleoclimate time series that they were looking at. There was quite a bit of leeway. If you look at these same authors and a later publication that they had, they used the following equation here. And so there is a basic constraint of the galactic year, but the reconstruction here is completely out of phase with the original reconstruction. So really these cosmic ray flux models, given that you can get results that can be completely out of phase, it's completely unclear what kind of useful information is being provided by these reconstructions, or if there are really any meaningful constraints at all on these values. So where do these Phanerozoic paleoclimate reconstructions come from that are being compared to these reconstructions of the cosmic ray flux? So I'm going to focus on a very recent reconstruction, the Phan-DA reconstruction, because they use the methodology that I actually was instrumental in inventing as my PhD. So this is something I'm extremely familiar with, so I can talk about it in a meaningful way. So in the Phan-DA reconstruction, they used 5 fundamentally different types of proxy data, but this basically aligns a really fundamental complexity here. So it's actually, as you go over these very, very long timescales, these proxy data, they're not the same species. So take, for example, these macro or microfossil carbonates. These are completely different species over different times. So we can't then take them into the lab, measure them. This is especially the case with conodonts, the second one showing here. They went extinct at the end Triassic extinction. So there's really nothing, and it's totally impossible for us to take these kind of worm-like creatures, and the image is actually showing their jaws and their teeth. But to take these creatures and grow them in the lab, see how they respond to temperature, see how their bones and their teeth respond to temperature, we just can't do that. And so there are some big assumptions we have to make in order to be able to use this data. Now, ideally, we would prefer to have data that comes from sediment cores. And so this means going into the ocean and drilling down into the sediment and extracting a core of that sediment and then making measurements on that sediment. So the advantage of that is that you can have fairly good dating. There's a continuous or relatively continuous deposition. And so you have relatively even data through time. But a huge problem for using this data, if you want to go back very far, is that the seafloor is of different ages in different locations. And the oldest seafloor that we can find goes back to the Jurassic. So there just isn't any seafloor that is older than that. So once you go past the Jurassic, then you've got to take data from geological outcrops. This has relative dating, has unconstrained unconformities, you have limited fossiliferous horizons. This is just a very different type of quality of data as you go further and further back in time. Another factor that you need to take account of is that the proxy locations shift around through time. So if you take a measure in a particular location in the present, it could be in a completely different climate going back through time. It could be, currently in the high Arctic, but in the past it was actually in the tropics. And so how you model, how you account for the fact that these proxy time series are shifting through time, that they're shifting through different climate regimes, while also keeping track of what the local climate they're measuring is, this is an extremely difficult task. Also, the details of the paleoclimatic environments really matter. So take, for example, a shallow sea area. So the delta 18O of the water within the shallow sea that the paleoclimate microorganism will be measuring, will be living in, that will later measure. This paleoclimate proxy, it really matters where exactly it's living. Is it close in this shallow sea? Is it further out towards the open ocean? Because the delta 18O signature is going to be very different. So how you then do your reconstructions of the where the continents are and where specifically these proxies are lying in relation to, say, like an open bay like this also really matters. But as you go further back in time, the location where we have reconstructions of the continents are pretty uncertain, pretty wildly uncertain. So just to take these two little maps that we're showing here, even though they're for the same time period that I'm showing on the screen, right? The geologists reconstruct them differently. There are different latitudes, there are different longitudes, the shape of the continents are a little bit different. And so because these little environments matter, this is a big deal. So the uncertainties for these reconstructions are actually quite large. So one criticism that I have of the Fan-Dié reconstruction, even though I think the authors did the most that anyone has done so far in trying to account for all the factors that I just talked about, is that their paleoclimate proxy uncertainties are actually, in some cases, or in many of the cases for their proxies, are actually 2 to 3 orders of magnitude smaller than common era proxies. These are proxies over the past 2,000 years. These are the proxies, the common era proxies are some of our best data that we have. So the fact that they use such smaller uncertainties means that in my opinion, they really underestimated the uncertainties of the reconstruction. But given that we can't do anything about that, let's just take this ensemble of reconstructions. I've drawn an orange line around here to give us a sense of what the uncertainty is going back in time. And I'll note that these uncertainties are huge. So if we take, for example, a climate of 15 degrees Celsius, which is approximately what the contemporary climate is like, and we compare that to a climate of 40 degrees Celsius, which a whole bunch of times in these reconstructions, it could be one or the other, one of these two. These are radically different climates. 40 degrees global mean, annual mean climate is just completely different than 15 degrees C. So the uncertainties here are just so huge. So given that we have these huge uncertainties in the phasing and even the amplitude of the cosmic ray flux, these big uncertainties in the reconstruction, I just think this claim, this part of the hypothesis, is simply basis given the uncertainties. Okay, hypothesis part 2. So solar variability has caused 1/2 to 2/3 of observed global warming. And we're going to go through each of these mechanisms. So the first of these, solar ultraviolet irradiance, as I mentioned at the beginning, the variance is larger for the UV wavelengths than it is for the visible. We have observed that ozone varies by 1 to 3% due to the solar cycle, but this really just doesn't have a very big impact. So people have looked at this, and if you're interested in the circulation of the stratosphere, say second or third order effects on the circulation of the stratosphere, then this is an interesting thing. But the fundamental problem is that radiation in the stratosphere preferentially goes to space. So if you heat the stratosphere, then it's just the photons are just going to go to space. And so it's very, very hard to do something in the stratosphere and then have it have impacts down at the surface, let alone, say, the mid-troposphere. So because the theories that have been proposed for this are relatively, underwhelming, I'm not going to spend time in going through these hypotheses. So I'm going to move on to part B here, the hypothesis part B. And this is the direct effect of total solar irradiance, and especially how it interacts with the ocean. So again, as I mentioned at the beginning, we would expect the ocean to absorb about 90% of any energy imbalance of the climate system. And so this is a reasonable place in principle to look for this phenomenon. Okay, so I'm going to be looking in detail at the following paper and the claims made by these authors, but these are emblematic of several similar papers that I'll also be talking about, but more briefly. So this one I'm going to reproduce the results and walk through and show you some of the things that I think are very problematic about this reanalysis. So there's analysis the authors did. So what they did is they tried to create a model that could describe global mean sea level. And so they said that the dominant forcing here is actually solar variability, followed by Nino 3.4, which is an indicator of the El Nino southern oscillations. This is an extremely important phenomena within the climate system. So they said solar variability is more important than Nino 3.4. This is their claim. So how did they get to here? So they took the original global mean sea level data, and I'm going to note that I'm using for all of my analyses, I'm using the most recent version of the data. So in general, it looks very, very similar, but there are some differences given the updates to the data. Okay, so the authors removed the trend. So this trend seems to me pretty obviously driven by global warming, but for the authors, they think that this is unimportant, so they remove it. Okay, we're going to remove the trend. What does global mean sea level look like then? Okay, we have this particular time series oscillating back and forth. All right, so what could be driving this? Just if we look at the bare data, right? This is what I would give to my students, as the first assignment. Okay, just look at the data. What do you see? So if we just look at the data, this original data, Nino 3.4, the TSI, the total solar irradiance, as well as the sea level, then we can see that the green line, the Nino 3.4, is matching the global mean sea level pretty well. It seems to be doing a pretty good job. When I then look at the TSI, just by eye, even though we should look at this, obviously, any analysis in statistical rigorous detail, but simply by eye as a first check, TSI does not appear to be driving this really at all. It really seems to be driven both at the shorter scales and the longer scales by the Nino 3.4. So how was the underlying data processed? What did the authors do? So what the authors said they did is that they took a 1-year moving average of the global mean sea level, as well as they say 1-year moving average in Nino 3.4. It's actually not the case. So the authors appear to have at least made a mistake in that regard. All of their plots and all of their results actually show a non-smooth version of Nino 3.4. So they just didn't do that. So showing now the smooth TSI reconstruction. And so what they then did is they ran these time series through a chi-squared linear model fitting procedure, and they allowed the TSI phasing to be a free parameter. So here I've plotted the actual TSI, or smooth version of the TSI. The authors of the paper actually let it be a functional form and allowed chi-squared model fitting to shift the phase of the TSI to be whatever it needed to be to match global sea level. So the fitting happened to shift it by 1.5 years, and if we look by eye, yeah, it does seem to do a much better job if you shift it by 1.5 years. The authors then claim that this is a fundamental feature of how solar variability influences the ocean, at least the surface ocean, and that this is some fundamentally important time scale for this particular process. But we could step back and say, should we even be doing this type of analysis here? So the short answer is no. Why? Because this data is autocorrelated, extremely autocorrelated. So what's the problem with data being autocorrelated? So chi-squared model fitting, just like linear regression, assumes that the data samples are independent. But autocorrelated data isn't independent at all. So technically, autocorrelation means that the coefficient covariance matrix is non-diagonal. So if it's non-diagonal, then the equations that are used to actually compute these that are actually used in the software when folks run these types of calculations, these equations no longer apply, and the parameters are going to be meaningless. The degrees of freedom are going to be off, and so we're going to receive confidences that are just simply meaningless. So given this extremely high autocorrelation, this is highly problematic. What we would want to see here is a lag of 1. We would want to see a correlation that is statistically equivalent to 0. So instead of being high like all these values are, going out to many, many lags, 50 lags in the case of sea level, then we would want to see this be 0, but that's emphatically not the case. You can actually do formal tests, which I've done on the model residuals, and this basically is the model here is just nonsense. Okay, the variables here are also strongly autocorrelated, and in the analysis that was done here on the right, the authors did the same chi-squared fitting procedure. I'm just going to blow up the significance values, and these are just simply absurd values. Having a significance of something like 16 sigma just does not make any sense. For anyone who has any experience doing regression analyses, chi-squared fitting, anything like that, confidence intervals on climate data, earth sciences data, this is just absurd. And this is due to violating the statistical assumptions that go into this type of analysis. Now, in my background research, I found that this is extremely common. I was surprised to see it in paper after paper after paper. I looked very closely at their methods and found invalid regression analyses, invalid chi-squared fitting, and many of the climate solar variability papers. So this is just a big problem for the community that claims that solar variability is extremely important for climate. Okay, so if sea level itself isn't explained by solar variability, maybe the derivative of sea level. So in this particular paper, the authors compared the derivative of sea level, so sea level change rate, with the total solar irradiance. And so it's based on 20 stations. So I'll just point that out here. Is using 20 stations to find this great correlation, is that a good idea? Well, let's look at satellite measurements of the sea surface height. And so what this video is showing is a compilation of several months actually many months over several years for sea surface height changes that have been observed using satellite data. And as we can see from this particular data, it really does not make sense to take 20 particular locations at locations across the globe, just in coastal locations, and say that this represents the global sea level. So if we go back now to the data, and so what this is Aviv from the department is reproducing the results. So he went back and he found the 20 tidal stations that were used, and that's shown in the yellow or gold line, and comparing with TSI. And so what he did find is that over the period of analyses, there's that the authors had in the publication, there's a kind of rough correlation. But then if you look after that time period, and then especially if you look in satellite data, this correlation just simply goes away. All right, so what about ocean heat content? So it's also been claimed that ocean heat content is related to TSI, and these, and just like the other previous situations, if you compare it with contemporary satellite data, these relationships just simply go away. All right, so I think given all these arguments that I've presented, it's obviously not completely exhaustive of every paper that has touched on this, but among the major papers, especially the ones I know that you folks are familiar with, I just don't find this convincing. So the evidence here is just really lacking. The analyses are poorly done, and they just haven't been, we can't verify them with contemporary data and trying to reproduce these results. All right, so now let's turn to this part C, 2C here, this mechanism C. And we're going to look at how galactic cosmic rays could potentially covary with cloud condensation nuclei. So I want to just start off with kind of a statement about fundamentals of clouds. So CCN are not a dominant control in the formation of clouds. So cloud formation is not CCN limited. If you compare the distribution of CCN to the distribution of cloud cover, there's not any clear relationship here. So if we're looking at the cloud cover where dark is very little cloud and white is a lot of cloud, and we're looking at the CCN concentration, there's just not really any pattern connection here. And that's because cloud formation is not CCN limited. So just as a kind of statement of fact, this is important as we're kind of thinking through the argument here. So what does describe this? Well, the fundamental principles of clouds, water vapor, and where the storms are. So if we look at the tropics and we compare the water vapor in the tropics, so roughly 30 north to 30 south, and we compare that to where the clouds are, we see that where we have a lot of water vapor, say in Indonesia, Papua New Guinea, then we see high clouds with a lot of water vapor. Whereas say we look in the Saharan desert and there's very little water vapor, very little clouds. If we move outside the tropics and we're looking at the exotropics, storms describe where the clouds are, right? Storms are made out of clouds. And so where we have storms can, in the storm tracks, can explain to first order, where we see clouds. So now let's turn towards the mechanism. So for the galactic cosmic rays, the idea here is that as they come into Earth from supernova, then they generate positive and negative ions in the atmosphere. And then the idea here is that these ions would help stabilize small clusters of vapors. So this is non-water vapors. Okay, and then two options could happen. So if these new particles coagulate with existing CCN, then we get no new CCN. If these new particles grow by condensation of other vapors, then we get new CCN that are formed. And so if we have new CCN that are formed, then it would be possible to increase cloud reflectivity, cloud lifetime, as well as the effect of cooling climates. This is the most important effect here is called the Toomey effect. And on average, this is a real thing. You add CCN to a cloud area, and the clouds on average do tend to get a little bit more brighter. So insofar as this argument goes, the logic of it is a reasonable kind of logic. The question is, does this actually happen in significant amounts in the real world? So we've had direct tests of this, especially with the cosmics leaving outdoor droplets cloud experiment, which I'm showing some of the results from that. And what we see is that on a global average, if we look at solar max to solar min, then there's only a 0.2% change globally. So this is the case if we look in pre-industrial, it's the case if we look in present day. These changes are very small. So in some locations, it could be a few percent, say like Antarctica where we don't have many CCN, but even that is a tiny value. Why is that a tiny value? Because normally CCN concentrations vary by orders of magnitude. So if we just take this particular location, which is in Oklahoma, and they took 5 years of measurements of CCN. And the mean was 2,000 cubic centimeters, but the data, day to day, varied by orders of magnitude. So CCN concentrations normally vary by huge amounts. A change of 0.2% is just very small. And then if we think about the radiative effect, then the radiative effect is small even for big changes in CCN. So what this particular paper is showing is a cloud resolving model experiment. And so what the authors did is that they ran this cloud resolving model with different CCN number concentration levels. And so what they found is they doubled CCN. There was never more than a maximum change of 0.15 watts per meter squared for a doubling of the CCN concentration, whereas CO2 forcing is 2 watts per meter squared. Right, so even if it's a doubling, let alone a 0.2% change, even if it's a doubling, we're still an order of magnitude too small. You can look at this in another way. So this particular work is using satellite data, and we can use the particular CCN or aerosol sulfate. And just as an example upper limit to this, let's take that 0.2%, multiply it by 10. So increase it by an order of magnitude, and then say, what is the radiative response to this? So in the global mean, this is 0.03 watts per meter squared. So 2 orders of magnitude, too small, even if we take the 0.2% and increase it by an order of magnitude. So insofar as the radiative mechanism as a fundamental idea, it just doesn't make sense. Changing CCN concentrations by these tiny amounts will just have almost no impact on the climate system. I will also point out what I said at the very beginning. Cosmic rays just don't obviously explain global warming. It would be an extremely exotic mechanism that takes an oscillating signal and then converts this into a trend. All right, so far as the second part of the hypothesis, I just don't see the evidence here. The fundamental arguments are just simply lacking. And I want to go back to the idea of these hypotheses are really very extraordinary. So the extraordinary claim that climate over the Phanerozoic is determined by cosmic rays, that climate over the past 100 years, that we can explain 1/2 to 2/3 of global warming by solar variability, these are extraordinary claims, and they require extraordinary evidence. For the solar variability hypothesis, there just isn't even reliable evidence. Okay, so what is an alternative here? So as a first order explanation of trends, CO2 does a great job. So we're going to get into more detail. This is not the end of the story. I've made criticisms of people who correlate, paleoclimate proxy time series with other things, and so I'm going to do more than a correlation here and go into the fundamental physics. But not only do we have this observational data of the CO2, but we know this observational data is reliable because we know how much carbon has been emitted, right? Fossil fuels, coal, natural gas, oil, these are extremely valuable global commodities. And especially since World War II, there's been a dramatic increase in the emissions of these. And that's exactly when we've seen this rise in global temperatures. So we know where they're coming from, fossil emissions, as well as land use changes. We know where they're going. So about half of it's going to the atmosphere, about half is being split between the ocean and the land. And so there are, especially go back prior to the 60s, a little more uncertainty in the sinks side of this equation, rather than the part of the equation, the sources that people were very meticulous about gathering this particular data that was very valuable to their business. But within uncertainties, we can explain what's going on, where has it come from, and where is it going. But insofar as the fundamental physics, right? Like, why would we even expect there to be a global warming in response to CO2 emissions? Let's get into that. And let's get into it by looking first at a very simplified model, Mars. So we're going to take the atmosphere of Mars is 95% CO2. And if we look at its emissions from space, then we see a very interesting feature. We see this ditch that's taken out of its emission spectra. If we remove that ditch, it looks remarkably like a black body. So we would expect a planet without an atmosphere to have essentially a perfect black body emission. But because of Mars's atmosphere, we have this ditch that's taken out. And so this ditch that's taken out, this actually has the effect of warming the surface of Mars. So because Mars's atmosphere is relatively thin, this is not much of an effect on Mars, but it's much more important on Earth because of our thicker atmosphere. It's even more important on somewhere like Venus, which I'll mention a little bit later. But let's go to an Earth-like planet here, and we're going to see what is the fundamental physical process that drives warming for CO2 or other greenhouse gases that are in an atmosphere. So we'll start off here with our no atmosphere planet, and it has a surface temperature pretty chilly of 259 Kelvin. It has an ingoing and outgoing IR flux, so long wave flux, or the radiative flux that's coming in and out of the system. It must be balanced. So what's going out must equal what's coming in. Otherwise, we would violate the second law of thermodynamics. So this is the baseline case. Let's now see what happens when we add CO2. So we've added CO2. That's approximately what current levels of CO2 in the atmosphere are. What's changed? So right now it's out of energy balance, but the outgoing, so because it's out of energy balance, the temperature is the same, but the outgoing flux has gone down, right? Because we've taken the chunk out of this emission spectra and we're now emitting less to the atmosphere. But this is out of balance, so we've got to come into balance, and the only way we can come into balance is by increasing the surface temperature of the planet. And so this increases the temperature. Now we're at 267 K, and we've balanced the incoming radiation with the outgoing radiation. All right, now what happens if we add all of the greenhouse gases and we have it be an energy balance? Then we come to a much warmer surface temperature, 288 Kelvin. The ingoing, again, is matched with the outgoing. And this is really the fundamental physics of the greenhouse effect. Why, when we're adding greenhouse gases, do we see this? So we know this data, it's observed from satellites, looking from space down to Earth. We see that these chunks are taken out of the emission spectra of Earth. We can then take, these chunks that are taken, these bands, or this like continuum kind of sections, especially by water vapor, and we can actually measure these things in the lab. We can measure different gases. We can measure their radiative properties, and folks have done this to extremely high accuracy. It's a great database, HyTran database, where you can go and look at all sorts of gases and all sorts of conditions to see, what's being absorbed with these particular gases. So we can look at the emission spectrum of Earth, and we can say, we see the effect of gases that are radiatively active, especially water vapor and CO2. So there's an important distinction between these two. So water vapor, H2O, just has a short-lived time scale in Earth's atmosphere of approximately 10 days. So the hydrological cycle is relatively fast. The CO2 has a much longer time scale, so an E-folding time scale of tens of thousands of years. And this is because the geological processes that cycle carbon within the atmosphere and then down into the rocks and through the crust of the Earth and the mantle of the Earth, then this is a very long process, whereas the hydrological cycle is a much, much faster process. So this has very important implications for the importance of these gases. So for example, if you take out CO2 from the atmosphere, what happens? Well, in this simulation, the authors pulled the CO2 out of the atmosphere and Earth rapidly froze. What would happen if you pull out a water vapor, which folks have done? You pull out the water vapor, and because the hydrological cycle is relatively fast, then the Earth within a few weeks recovers to where it had been. So it really is CO2 that is the dominant control knob on how on setting the climate system, right? So given that we have the sun that's giving us energy, and then we say, okay, well, once we take that energy from the sun, what are the gases in the atmosphere that control what the climate is like? CO2 is the principal control knob because of this long time scale that it has in the atmosphere. Okay, so not only do we have this in observations, but we can actually derive from essentially first principles quantum mechanically why the CO2 absorption band takes this particular angular shape. So it's due to Fermi resonance. This is a quantum resonance in the case of CO2 between a symmetric stretch mode and a bending mode. And so this is the fundamental quantum mechanical basis of this. And if you're interested, you can look at this paper where this is derived, on pencil and paper. So not only do we have, observational constraints on how CO2 is related to climate, not only do we have the lab-based measurements and the satellite measurements that explain explicitly how the greenhouse effect is working, we can derive this from first principles quantum mechanically. Okay. Let's now put this all together, and we're going to put it together using a climate model. So we're going to take a climate model and we're going to ask two questions. What are all the ways that climate can change? And which of these explains global temperature? So this is the observed time series that I'm showing in black. And this is changes in Earth orbit. So this is what I mentioned at the very, very beginning of the talk when I talked about the Milankovitch forcing of ice age cycles. So ice age cycles are much, much longer than the past 100 years or so. So over the past 100 years, this is not an important factor. Solar variability, not an important factor in this model simulation. Volcanic eruptions, so short-term big impacts, long-term not so much. If you take all of these natural factors combined, does it explain the trend? No. To describe some of the variability, yeah. Okay, now let's look at human factors. So deforestation, farming, building cities, land use changes. very slight cooling. Ozone pollution, not much. What about air pollution? This is a cooling effect. It was because we emit aerosols. On average, these aerosols tend to cool. So this is their effect. If we put greenhouse gases into this climate model, what happens? Well, we see this nice trend, but it overestimates what's actually observed because there are other things that are going on. So let's add all the human factors. We describe the trend pretty well. If we add in these natural factors, we describe this variability even better. And if we were to add even more factors, especially something like an exact kind of reconstruction of the El Nino Southern Oscillation, then we would get this time series even better. So as a whole argument, climate scientists have been constructing, all of this work, putting it together, finding all these pieces, thousands of scientists for decades to put together a coherent story for why we see the changes that we've seen over the past 100 years, as well as at other timescales into the past. And so this provides a compelling, I believe, and coherent story. This is not something that's based on a kind of flimsy evidence and shoddy data. This is really a very comprehensive thing. You can read the IPCC reports of thousands of pages if you want to read all their different varieties of the reports, going into great detail. I can make this talk exceptionally long by mining that thing. But just as simple, straightforward, first order explanation, what causes global warming? This is essentially a solved problem. So it doesn't mean that all aspects of climate science are solved, but insofar as explaining global warming, we have a coherent story. We have something that we can explain from fundamental physical principles.